Uh, uh, Thank you very much, Maria, and thank you so much to the organizers for this great conference. Like AlCoVE is unironically my absolute favorite conference, so I'm very honored to be a part of it. So I'm going to be discussing some joint work here. So Tatyana and Ava and Leigh are some of my graduate students. So this particular thing I'm going to be telling you about is part of a joint project with Tatyana and Ava. Leigh hasn't been really working on this exact thing, but Leigh has been helping me in another regard. Leigh is a co-developer of a piece of software that I'm going to be using in this presentation called Dimerpaint, which addresses some of the things that are a little bit difficult to do in Minecraft, which I'll elaborate on shortly. Also in the co-authors area, a lot of this is going to be distinct older work of mine, joined with Amin Ghulampour and Martin Kuhl. I have some people I very much need to thank. So I'd like to thank my son, Ira Young, for Minecraft technical assistance, all of the really difficult things that are going to happen in this talk were not my technology, but Ira's, and also Arya Ye, who showed me how to set this all up, all of the streaming equipment and OBS and all of the various things. So I'm actually using Minecraft on my Nintendo right now, and I'm capturing the video and sending it out to you over Zoom. So I'd like to start by describing this object here. So what we want to do is we want to count these things. So to start with, there are three plane partitions here. I trust you're all familiar with the notion of a plane partition. So think of, if you're not, think of a plane partition as a stack of boxes in the corner of a room, much as an ordinary partition has a Young diagram, which is a stack of squares in the corner of a two-dimensional room. And I basically just want to count all configurations that are like this. So what do we have here? We have three plane partitions. There's a green one, a red one, and a blue one, and they all overlap here. So the green one's corner, in this case, I guess in ordinary XYZ coordinates, the blue one is centered at the point. I guess it's probably 220, right? Something in the XY plane, and the green one, I suppose that would be 202. Its center here, sort of where my red cursor is. And similarly the red one, and they all overlap sort of at this region in the middle. The rule is the white boxes, incidentally, are supposed to be thought of as being a part of all three plane partitions: the green one, the red one, and the blue one. They're common. This box here is in both the green one and the blue one. This box here is in both the blue one and the red one. And the rule is that in the region where the partitions could overlap, they must. So out here at the sides, it's okay to have just green boxes that aren't part of the other three plane partitions. But in here, all of the boxes must be in at least two of the three configurations, either all three like these white ones, or this box here is in just two of the configurations. It's a little bit elaborate to say exactly how I want to weight these, but essentially I loosely want to think of this configuration as being counted by 2 to the number of boxes, or q to the number of boxes which are present. So here, maybe I'll just kind of look up here at the sky a little bit so that I can write. So we want to compute this sort of a generating function. I want to sum over all configurations like this. And I basically am going to be adding up q to the weight of pi. And then there's another factor, which is a power of 2. Essentially, well, 2 does something else. I don't want to get into the details. There is a natural generating function for these objects coming from algebraic geometry. And the surprising fact is the generating function has a beautiful product formula, which I'll write here. So this m of q, this is McMahon's generating function for plane partitions. It's it's a big infinite product. It looks like the generating function for regular partitions, but everything gets raised to the power I as well. And this thing is the generating function for boxed plane partitions. Boxed A by B by C plane partitions. So I'll look up at the sky a little bit more so that you can see what I wrote. So yeah, this is, again, McMahon came up with both of these generating functions, you know, at the turn of the last century, and they're both simple product formulas. I didn't say what A, B, and C were. Let me just do that really quickly. So there is a sort of a parameter to this this problem, a couple of parameters, and they sort of have to do with the sizes of these rectangles, i.e. the offsets for where the plane partitions are. So I don't know, I forget my conventions entirely, but one of these numbers is A, say this one. Oops. Tech is too difficult. This number, the length here is A. And then this length down here is B. Right. And then C is, you know, B is also the height of this rectangle over here. A is not meaningful, but then C is the depth. So it's this sort of surprising product formula. So this appeared in as I say, older joint work with myself and Martin Kuhl and Amin Gulampur. The reason that this problem came up was, you know, maybe unsurprisingly, algebraic geometry. Maria asked in this picture, A equals B equals C equals 2. That is correct. Yeah. So the generating function here would be, oh, and I dropped a square. I should have said McMahon of Q squared times McMahon. Well, I didn't tell you what half of this stuff is anyway. But whatever, yeah. And in this case, A, B, and C are all the number 2. So you might know that there's 20 plane partitions that fit inside a 2 by 2 by 2 box. So if you just brute force count up the first few of these and then divide them by 2 copies of McMahon squared, you'll end up with this thing with 20 terms, and there are going to be various powers of Q. We noticed this experimentally. My colleagues noticed it when they were doing some geometry stuff. Specifically, it comes from the generating function for, I believe it's rank 2 Donaldson-Thomas theory, and a certain local contribution to that theory. But nonetheless, it's a pretty combinatorics problem. It has something to do with plane partitions, and you can tackle it naively. So my colleagues have a wall crossing proof, essentially, of this theorem, except that the thing that they prove it's equal to isn't this box counting stuff. It is, well, no, I guess that's, no, it is that. So there's a geometry proof that this is the correct generating function for these objects, and we would like a purely combinatorial proof. And it's always been sort of clear roughly how you should do that. And it's also been quite clear that it's going to be a lot of work to do it. The tactic is to transfer this problem to the double dimer model. And that's what's in the title of the talk. So I want to start by telling you about the double dimer model, like basically what the words in the title mean, double dimer and tripartite. Then return to this problem and show you how the setup works. In tackling this problem, it became clear to us that a lot of the fancy geometry was sort of a distraction. There's the idea here is going to be that you do a lot of work to transform the box counting problem to the dimer problem. And then once the problem is stated in terms of the dimer model, some results of my past PhD student, Helen Jenny, which were actually reported at AlCoVE 2 years ago by Helen. Some of the past results that she was able to obtain give you a recurrence that the generating function should satisfy. And it's recurrence that alters the parameters A, B, and C. So this gives you a sort of an inductive way to do the proof for no work, except you front load all the work. And the computations really are very, very, very hairy. So we wanted to find a way to streamline some of it. The streamlining that we're going to need comes from the fact, that the combinatorics happening here are really a lot simpler than the fancy geometry. There's a simpler underlying core of it. Anyway, let's start by look at my television for a bit. Let's start by going over to the Dimer model display. So if you were here at AlCoVE last year, you have probably seen this, and I will then show it to you again. So the reason there's the word square there is because I'm going to do a perspective trick. Hope this works. So yes, this is the square double dimer model, and it's not tripartite at all. It's just an instance of the double dimer model. In fact, first of all, I am going to show you the single dimer model. So here we have the square lattice, just d squared, and I want to think of it as having edges that are nearest neighbor. So all horizontal edges and all vertical edges is a piece of graph paper. Here is a dimer configuration on z squared. So what we have here, this object here is a dimer. Yes, I keep using the wrong pen. So this object here is a dimer. I think you should think of the word as being the same as polymer, but there's only two of it. So it's two vertices bonded together. And what I have is a covering of the square lattice with dimers. If you like, it's a perfect matching is another way of saying this. I want to then say what a double dimer configuration is. Well, here's another dimer configuration. If I stand on this plate over here, there's a different and unrelated dimer configuration on the same graph, the square graph. I'm just going to take this block of red concrete here and deposit it, if I can remember how to do that. There. So now there's something on that pressure plate holding that configuration on. If I go and stand on this one, it'll show the two configurations at the same time. This is a double dimer configuration. So what we see here is a collection of doubled edges and closed loops, which when you think about it is what you should expect to see. A dimer configuration has every vertex of degree 1, right? Each one is paired with something else. If I just superimpose those with multiplicity, each vertex is going to be of degree 2. So what can you have in a graph of degree that's everywhere degree 2? Well, I guess you can have edges that are connected to each other or edges that aren't. And if they're not, if this vertex is of degree 2, it's going to be connected to another one of degree 2. It's just going to get a bunch of closed loops. And as stated, essentially all of this connectivity is possible. The dimer model typically has some nodes. So in this case, what I'm going to do is I'm going to go around the backside. I'm going to leave that perfect matching on. I'm going to just fly around behind this wall here. I've colored in a perfect matching, and I've just made it with these edges that are sticking out from my wall a little bit. I've added a perfect matching which misses two vertices. Specifically, this, oh, my Minecraft is frozen. Uh-oh. Having technical troubles. Is the screen frozen for everybody?
The Minecraft screen is frozen, but we can still see you moving around like in the corner.
Curious. Let me just do something here. Okay. Well, why would that happen? Yeah, this is the right. This is the trouble of doing a high-tech talk. Let's see. Let me just try something. Unplug that and plug it back in. Then we're going to Didn't fix it, so we're going to delete that. I'll have to
It's truly
yeah, I'm just going to put in a video capture device.
I mean, and exactly this, darn it, that was working yesterday. It's that feeling where you've been working on a proof and then you go home with the proof in mind and you come back and you find the mistake tomorrow.
Oh, I can't believe it. That actually worked. Okay, amazing.
Was it a reboot?
Yeah, I just had to turn something on and back off again, or off and back on again, and then I had to rearrange some stuff in my streaming software. So we're now good.
If
right?
only proving theorems was that simple.
Yeah, I know.
All right. Yeah, take it away.
Yeah. And then let's see here. So do we have, yeah, and we even have my annotation. Great. So, okay, what was I doing? I chose a perfect matching which misses this vertex and this vertex. And otherwise it's got like this edge in here, that edge in there, and so forth. And as a result, when I overlaid a second perfect matching by stepping on my platform over there, what I got is a double dimer configuration that's doubled everywhere except in these two vertices. And the result is that there is a path that is formed between those two vertices. When you think about it, that's what is going to happen. Those two vertices are going to be called nodes and will play a role in the rest of the math that I'm about to show you. Let's delete the annotation. Okay, that's nothing. That's a thing from a past talk. Yeah, all of the stuff that I made from for AlCoVE last year is just over there. So a lot of these things are sort of time consuming to make, and you don't want to make them more than once. So next, I should show you how to translate between plane partitions and the Dimer model. So in fact, the way that you do this is always going to give you the Dimer model on the hexagon lattice, the honeycomb. So here's a big plane partition. I've decorated all of the faces of this plane partition with this picture. It's a picture of one Dimer and a fragment of the honeycomb lattice. And there is a perspective trick that you do. I'm just going to walk away from this in the sort of the upward direction. And once I get far enough away, you start to see a perfect matching. So that's again, there's one Dimer, the one on the top, and what it's lying on is this honeycomb graph. So there is this connection, and it's sort of folklore. There's probably way easier ways to say what this is, but this is the connection between plane partitions and tilings of the plane by lozenges and perfect matchings on the honeycomb graph. So there is a relatively natural way that one might expect to see the double dimer configuration, or the double dimer configurations that I showed you showing up, and that would be by simply superimposing two plane partitions. And so that's what I've done here. So here what we have is a plane partition. I think it's basically a slightly smaller one. I haven't drawn the honeycomb graph. I've just drawn the perfect matching edges. So over top of that, I've drawn a second plane partition, essentially arbitrary and unrelated to the first one. The second one is made of these transparent blocks here. So if you like, there is some of the boxes are in common with the blue partition in the back. So the second plane partition is these ones here. You should think of it as having a long, maybe even infinite arm there. And then up here, there's like basically a sort of a 2x3 upright rectangle of boxes there. And then the back wall of the plane partition I've drawn here. So these plane partitions you're supposed to think of as stacks of boxes in the corner of a room. And it's quite important to draw the room as well. So what you do is you imagine those walls, the three walls in the back, as extending to cover the entire plane, as well as this transparent wall. It's extending to cover the entire plane. So if one of these surfaces, one of these flat planes is present in both plane partitions, then I have drawn a doubled edge there. If it's only present in one of them, I've drawn the corresponding single edge on them. And once again, there's a perspective trick. Now, I've cheated quite egregiously in the placement of the red edges. And that's because if you view it from a very specific point in my Minecraft world, again, there's a perspective trick which happens. There it is. So here we see a double dimer configuration. Now this one has nodes, and the nodes are out at infinity. So you should imagine this path is just continuing to zigzag off to infinity like that. And similarly, there's another path down here which is going to continue off to infinity. There's a path here which comes in from up top, kind of moves around like this, if I can draw it correctly on my pad, and then exits out this way. Everything else, there's a simple closed loop here, which has got made of just these 3 hexagons, and everything else is doubled edges. So that is one situation in which you might expect to see the double dimer model arise when you're thinking about plane partitions, simply from superimposing 2 plane partitions. I should add, I'm sort of kicking myself because I didn't make a model of a tripartite one of those for this talk. Tripartite, I had quite a delay from my technology failing there, so we're probably not going to get to define or do all of the things I wanted to do today. One thing to notice, if you will, a perspective trick was necessary in order to see the dimer model appearing. There was one surface behind another. And so it's going to be a recurring theme that these dimer models really have a height to them, a good way to draw a picture of anything regarding the dimer model is to include this sort of third dimension that tells you where the plane partition is. This is a bit of a cartoon. The turtles are incidental to the picture. That is not an important part of the talk. They just keep showing up because I chose to make this thing out of sand. This is an example of a configuration with nodes around the edges. There's a bunch of blue nodes, a bunch of green nodes, and a bunch of red nodes around the top. And I guess there's a bunch of turtles appearing and disappearing randomly. This configuration is tripartite because no node is connected to another node of any other color. No node is connected to a node of the same color, right? Some of the red nodes are connected to blue, some of the blue nodes are connected to green. So this tripartiteness in this setting is sort of a description of the non-crossing partition, which arises when you look at the double dimer model and only figure out which nodes are hooked up to which other nodes. If you want an example of a not tripartite one, I've got a switch here that I just have to switch over to not tripartite. Okay, what that did was, maybe I can show you what the switch did. It just raised and lowered a section in the middle of my model. Once it's on the not tripartite setting, you'll see by making that small local change to the height, the red node has become connected to the red node here. So these two are connected together and they're the same color. That's not allowed. So that's a non-tripartite configuration. And this isn't actually a picture of the dimer model. It's just a picture of some other surface whose level curves have this connectivity property. The ones that actually come from the dimer model have these other curves added as well. Again, not an actual picture of the dimer model, it's sort of cartoon of it, but we similarly have these closed curves here. Those correspond to those can arise in the dimer model when you have those small closed loops. I would still consider this a tripartite configuration because then the edges that go between the nodes do have the desired connectivity. So skip that thing. I'll skip that thing. Let's just go back over here to the configuration that I showed you at the start of the talk, the one that I said that there were McMahon many of, basically McMahon squared times different McMahon. It was this. So I want to describe how to convert this to the double dimer model. So right away, there's a little bit of a difference. There's 3 partitions and not 2. And so the thing that you need to do, the trick is to rearrange it a little bit. And the rearrangement I've put over here. So for that to load. Essentially same connectivity, or same, not connectivity, but same combinatorics, like the same boxes are present. Here, what I want you to do is just forget the colors. So the only thing that matters is whether any box is, well, there's 3 places the box can be. They can be behind these walls. So a different part of my technology has failed. Just hang on. I'll just go and fix that. Everything possible to go wrong will go wrong. Great. So do I have my pointer back? Yeah, there we do. Okay, so all I want you to think about is whether the boxes are present or not. I don't want you to think about what colors there are. So you can break this down into 2 plane partitions. So one of them, I've included the walls for all 3 plane partitions. So this blue plane partition, for instance, it's a stack of boxes in the corner of the room, and I've just drawn the rest of the room. It's what this transparent piece is here. Similarly for the red one and the green one, those 3 walls intersect. And if you just look at the boxes that are in this new room with entirely transparent size, there's 4 of them in a little L shape here. 1, 2, 3, 4. That's one of the 2 dimer configurations. The other one is going to be in the back, and it's going to be made of all of the rest of the boxes. So we include these white boxes. Those are present in both configurations. And then we're also going to include all of these other boxes here. And when I superimpose those 2 configurations, and this is the part where Minecraft starts to fall down. It's very time consuming to make these special models. What I'm going to do is, in light of the fact that I've already had 2 tech failures, I'm going to do the most ridiculous thing possible. In particular, I'm going to actually just unplug my Nintendo Switch and plug it into another laptop to show you something else. So fingers crossed, let's hope this works. So that should have blanked the screen. And this should now be showing you my laptop. There it is. Haha, amazing. Okay, so this is Dimerpaint. So Dimerpaint was a paint program, sort of, well, it's what it sounds like. It's a tool for illustrating things with the Dimer model that I put together originally about 10 years ago, because it's just so time consuming to draw pictures for projects like this. What we have here in Dimerpaint on the left is the configuration I was showing you, these 4 boxes in a cube. And I should say also Leigh Foster has been helping me a lot modernize Dimerpaint and make it do other things. So this has been quite a bit of work over the past couple of years. In the back here, I have the other configuration, this red one, and that's all of the boxes that were in the red part, the green part, and the blue part here. Each one of these, as described, corresponds to a dimer configuration on the hexagon lattice, which I can turn on and off. And what I've done is superimpose those dimers to give you an instance of the tripartite double dimer model here. And it is sort of, it was initially mysterious to us why we had this connectivity where, you know, here maybe make all of these blue nodes, all of these red nodes, and all of these green nodes or something. So whenever you do this construction, this particular way of rearranging the boxes and coming up with these 2 very specific plane partitions and then superimposing them, you always end up with exactly this connectivity, the tripartite connectivity. Tripartite double dimer configurations are exactly what Helen Jenny's thesis was about. And so this is the tool that will let us do the operation. Maybe rather than saying the next thing that I was going to say, which is some conjectural stuff about how it is to actually streamline this whole procedure, I'll use the last 2 minutes to show you something about Leigh's project. Leigh is working on another problem related to the double dimer model, but it's otherwise unrelated. It involves the squish map. So this here is an example of a dimer configuration on the hexagon graph. There is another way to relate this to the double dimer model, simply by redrawing the way, or by changing the way that you draw these pictures. So if I sort of continuously perturb these hexagons, so as to make some of them bigger, some of them thinner, you gradually see a double dimer configuration appearing here. So there is, again, all of the same features can appear. There's a doubled edge here, and then there's a closed loop that goes around here. And for ages, oh yeah, Leigh is posting in the chat the modernized Dimerpaint there. For ages, I never really knew what to make of this map. So we're going to show, work is done and in preparation, that this is related to the SL2 double dimer model of my advisor, Rick Kenyon. So this map actually sends the single dimer model to the double dimer model, and we're finding interesting things to do with that. So I think that's it for me. I am going to just pop this back over to Minecraft to make it more likely that I can take questions. No.
Okay.
Okay.
Let's thank Ben. And yeah, we have time for a couple questions here. Let me go to gallery so I can see if people are raising their hands. If nobody else has questions, I have questions. Oh, I should spotlight this again. Sorry, wait. Okay. Yeah, maybe I can ask a question. So you started out with these the identity that multiplied the two McMahon formulas.
Yeah.
And you said you wanted a combinatorial proof of that. Is the claim here that, like, with this bijection to the dimer configurations, there you have a combinatorial proof of that?
I don't think so. No, it's still it's going to be, I guess, more combinatorial here, but it's not completely. So the issue, my screen share is broken. That's fine. The issue is that here, let me just maybe just close the window. Hold on. I can't answering the question. Yeah, so the way all of this is going to work is that to prove that the conjectured enumeration formula for these objects, we're basically going to use a version of graphical condensation, so Dodgen condensation. This is a recurrence which allows you to verify or to vary the parameters A, B, and C, which define where those red, green, and blue plane partitions overlap. And it's not an inherently bijective type recurrence. So all we're going to do is show that this generating function that I've written down obeys the same recurrence as the product formula that I've written down, and they have the same base case. So they're going to be the same.
But that would be then a more combinatorial proof than like
Yeah,
what was
everything is
before, basically.
Everything is is going to be slightly more combinatorial. That's right.
Okay.
And
then my other attached to this question is, can you say that maybe 1 or 2 sentences about what the geometry that motivates this is?
Yeah, so this it's a theory of enumerative geometry called Donaldson-Thomas theory. So the idea is you want to, in some sense, be counting curves in the space, with big scare quotes around counting curves and space. The idea is that you want to think of a curve as being cut out by an ideal in the space of functions. And the way that the plane partitions arise is when you think of spaces that have a torus action. So in that case, the computation in Donaldson-Thomas theory, there's this ATIA bot localization that lets you do the computation essentially as a discrete sum over plane partitions. And the reason for that is the plane partition is basically the same thing as a monomial ideal. So you take your space, you cut it up into charts with the torus fixed point in the middle of each chart, and the curve is now going to be cut out by a monomial ideal, i.e. supported at the origin. And a monomial ideal in 3 variables is going to be exactly the same thing as one of these plane partitions. So that's the reason that the combinatorics appears is pretty distant from the geometry. And I think from the geometrical point of view, the wall crossing argument that my co-authors have is probably more natural. It's telling you more about what's happening in the geometry of the space. Nonetheless, there's all of these interesting plane partition facts that fall out of this geometry, and my aim is to try and prove some of them combinatorially.
Cool.